Okay. So we know that CP is violated by delta CKM, but the strong CP phase also requires parity to be violated, and that's negligibly small. So we can ask a question, does the quark mass matrix, or equivalently the Yukawa couplings of the Higgs boson with the quarks, do they violate parity? Because theta bar is 0 or is very small. Now, if you are working on the minimum left-right symmetric model, then this question has an answer. The model won't tell us that theta bar is 0, but it will tell us that for theta bar to be 0, the Yukawa couplings must remain Hermitian even below the parity breaking scale. Anyway, above the scale, they are Hermitian. What it will tell us is that below the parity breaking scale, they must remain Hermitian. You can ask the same question on the leptonic sector. Here we know that Majorana masses and the seesaw mechanism violate parity. So we can ask the question, do the leptonic Yukawa couplings violate CP? This of course is $1 million question, right? So if you are again working with the minimal left-right symmetric model, what it will tell us is that if CP is also violated, then there is no protection because P is violated. And the strong CP phase is generated in one loop. And so basically it predicts that all CP violation in most of the parameter space, it predicts that essentially all leptonic CP violation, including delta CP, that is being probed by neutrino experiments must be either 0 or pi. Now this is a surprising result because the large mass scales, like the Planck scale or the LR breaking scale, they only enter logarithmically. So there is no suppression. So this result would apply even if the LR breaking scale is at 10 to the 15 GeV. In fact, it applies better at that scale. And it's shocking because if delta CP is 0 or pi, then what about leptogenesis? And what about grand unification? So we are putting the LR model to a very high challenge or a test. Now I don't know about the founders of the LR model who are all here except for Salam. Dr. Pati is here and Goran and Ravi are here. I don't know what they would think of the LR model being put to this test. So let me go and try to derive these results. So the LR model is based on the left-right symmetric gauge group as we have heard, and here are the founders. Now the triplet Higgses give the Majorana mass to the neutrinos. It has a bidoublet phi that has two standard model Higgs doublets, H1 and H2 that I've written. And the left-handed quarks are the SU2L doublets, and the right-handed quarks and leptons are the SU2R doublets. Under parity, phi goes to phi dagger and L goes to R, right? Now, if you have two Higgs doublets, you can expect CP violating term of this form, H1, H2. But what's interesting is that parity makes this term real because it just takes this term to its Hermitian conjugate. So mu squared has to be real. Now, this is an important thing to note because this means that there is no hierarchy problem in the imaginary part of there's no quadratic divergences which are CP violating. So the hierarchy problem and the strong CP problem basically separate out. So the fine tuning in the imaginary part is your strong CP problem, and the hierarchy problem doesn't contribute to it. That's what makes the calculations possible. Now, so what is the calculation? So theta bar, of course, is made out of two terms, theta QCD and the argument of determinant of the quark mass matrix. Now, theta QCD is absent due to P, and of course, because of left-right symmetry, Yukawa matrices are Hermitian. So the only way we can generate an imaginary part for theta bar, you can always choose the first Higgs doublets wave V1 to be real. So the only way is if the second Higgs doublet V2 picks up a wave in that bidoublet, right? So now there's only one CP violating term for it to pick up an imaginary wave in the LR model, and that is this term, this quartic coupling between the two bidoublets and the Higgs triplet. So when H1 picks up the wave of the order V scale and delta R's pick up the wave of the order VR squared, the imaginary part of alpha 2 generates an imaginary wave to V2. And of course, that wave has to be weighted down by the mass of H2, and that we know is alpha 3 VR squared. It depends on yet another quartic coupling, and therefore it cannot be more than 1, order 1. So here is the contribution to the imaginary part of the H2's wave. Now, how does that generate theta? Because when HT couples with H1 to give the top its mass, because H2 is in the same bidoublet, it couples with H2 to HT couples with H2 to give V2FF, and that has an imaginary component. That's the imaginary contribution to the B quark mass, and you divide by the B quark mass and you get theta bar. So it's a very straightforward calculation. I mean, I'm like missing some factors of 2, but basically you get MT by MB alpha 2 by alpha 3 to be theta bar. There's no suppression in this term. Now, theta bar being small, because alpha 3 is at the most 1, you put that value, and you get alpha 2i to be less than this. So there's no imaginary component to this quartic. So if you had these 4 Higgses of the left-right symmetric model, and you scattered them, you would expect CP to be violated because the Higgs sector is complex. But you shouldn't see CP violation, right? And that's the prediction, or you should, it's very, very small. Of course, these Higgses could be at 10 to the 14 GeV. So for this, we need a trillion TeV collider. And since it's Rabifest, for Rabi, it has to be a trillion TeV neutrino collider. So here these neutrinos collide. And of course, the magnets that power this collider are made out of U1 B minus L current. They are not made of electricity. And that's why the neutrinos bend and they collide. But this technology became obsolete 13.8 billion years ago. So what we have in stock today is the collider with virtual neutrinos, right? So you have virtual neutrinos now colliding, but this data is already known, and this data is known in terms of, is tabulated in terms of Feynman diagrams. So basically, it's the same collision. Here the neutrinos are virtually generated between the scale MR and M Planck, so it could be at 10 to the 15 GeV to 10 to the 18 GeV. We know the answer of this collision. It has to at least have this term, which is basically the radiative correction to the alpha 2 term that I was talking about. And that radiative correction is basically an imaginary part of these Yukawa couplings of the phi's and deltas with the right-handed neutrino. And these are all the neutral parts of these Higgses. So basically, it's a simple term. It's the imaginary part of this product, right? This Yukawa coupling. Now, these are all Hermitian matrices. These are the Dirac, the two Dirac-Yukawa type couplings in the leptonic sector. That would give the charged leptons and the neutrinos Dirac masses, and this is the Majorana mass. So these are three Hermitian, this is a product of three Hermitian matrices. H twiddle and H are Hermitian due to parity, and F dagger F is Hermitian. The product of three Hermitian matrices has an imaginary trace. And that's why this is a one-loop contribution. In the quark sector, you don't have Majorana masses, so it's just two Hermitian matrices. So you have to have a long string, like 6 of them, 6 of H twiddles and H's before you get an imaginary part, and that's a 3-loop effect. And these F's and H's are what generate delta CP, the Dirac phase of the PMNS matrix. So once they are their imaginary part, this trace is basically imaginary, and the imaginary part is the trace, is the commutator. So you get this, and what we will see is that in physically interesting regions, you just have to conclude that delta CP has to be 0 or pi. For example, we know charged lepton masses are similar to the quark down sector masses. So if H33, H23, the leptonic Dirac Yukawas are similar to the quark, then this product is like 10 to the minus 3. For sin delta CP to be, have an order 1 value, this term has to be very, very small. But then this term, like, but you want B minus L gauge symmetry to break at around the CISA scale. That's yet another physical ground. So this cannot be too large, otherwise you'll separate the B minus L gauge symmetry breaking scale from the CISA scale. So either taken together or even taken independently. In a large parameter space, basically you have sine delta CP being negligibly small. So that's what we are saying. And this, so if you have a TeV scale collider, you may not want to look at the, a trillion TeV collider, you won't look at the 10 TeV scale. But even at this scale, at 10 TeV, you would consider this to be around 10 to the minus 7 to 10 to the minus 8. And still, this constraint is still non-trivial, even for 10 TeV scale. So and higher the scale of left-right symmetry breaking, the stronger the constraint. So we are really probing, large scale left-right symmetry here, and most of the symmetry space, and this is what we conclude. Now I said theta QCD to be 0 because of parity, but that's irrelevant to what I said. Basically, because what I'm saying is theta bar one loop, that is too large. Now, so this has to be cancelled. Whether it is this, how this combination cancels, that doesn't matter. Parity, of course, sets theta QCD to 0, but even if it didn't, the problem still remains. So this is not really a necessary condition for what I talked about. Now if supposing the leptonic CP phases are 0 and alpha to I is 0, then, or like they don't exist, then there must be a strong CP reason for that, a solution for that. So here's the history of solving the strong CP problem. So in 78, Ravi and Goran suggested that the left-right model might solve the strong CP problem. But attempts to add more Higgses, more symmetries to prevent this alpha to I term, and more Higgses to break them didn't work. In hindsight, this actually makes sense, because had these attempts worked, it means that Higgs sector would couple both to leptons and quarks. But since that didn't work, and it would generate CP violation in both sectors. But the fact that they didn't work is actually important. Then in 96, of course, it was noted that SUSY solves the strong CP problem, because that alpha 2 term is just absent in SUSY. But I'm not going to talk about SUSY here. In 2010, I got reinterested in this. So the LHC was turning on, and at an 8 conference, a volunteer who also happened to be a physicist asked me what I thought we would find in the LHC. So I told her that maybe heavy fermions, because they can be naturally light. And then I thought we never added heavy fermions to the left-right model to see what they do. And it turns out that if you add them, they automatically solve the strong CP problem. Now you just impose both P and CP, so that alpha 2I is 0, and there's no CP violation. But the heavy quarks, like you can think of this as the 4th generation quarks, and then the and the chiral counterparts, which are right-handed, which are now also SU2 and doublets. So they'll have a direct mass term with the usual quarks, which can be CP violating. And that can generate CP violation in the Yukawa sector once you go below the mass scale. That CP violation essentially appears in the Yukawa sector. And since there is parity symmetry, all of these, and since there is parity symmetry, these will be, the quark mass matrices will remain Hermitian, even below this mass scale. Now what you notice here is that there's no leptonic CP phases generated, because you are breaking symmetry in the quark sector, not in the leptonic sector. So I just have a couple of more slides. So in the leptonic sector, you can say, well, what about adding more heavy leptons? You could do that, but then there are 2 ways of doing that. One, you could add them with an intrinsic parity I, or without an intrinsic parity phase. So you have to always figure out an intrinsic parity. It so happens because of U1B symmetry, that choice is not there in the quark sector. So it automatically, there's no choice, it's automatically of this type. But now if the intrinsic parity is I, then P squared, which is an automatic symmetry because P implies P squared, and delta waves don't break P squared, they only break P. This symmetry is intact. And so the heavy leptons, actually the lightest of them is stable, and they could be dark matter candidates. They don't generate CP violation. So once again, we arrive at this result that leptonic CP violation is not generated in the left-right symmetric model, strong CP solving, even with this kind of lepton. Now, of course, you could add them with the usual intrinsic parity phase, which is 1, then it's generated. But if they are heavier than MR scale, they'll again generate these in one loop like we have seen. And that's not healthy. If they are lighter, then there's no effective minimal left-right model at any scale. And CP violation scale is generated below P breaking scale. And maybe you could discover these heavy leptons at the TV scale. So I think my time is up, but I've come to an experimental slide. And as you know, so I'll just also summarize this because here is the experimental situation of the Dirac CP phase. This I plotted by the year. So this is when data started coming out in 2012. So this is from NewFit, combining data from NoVA and T2K. So this result of 197 is where we are right now. And it has the central value has moved around, but the error bars are still large. And so we are waiting for more data. Yeah, I just also put a reminder to myself that there's a talk in the strong CP problem, so we do have to mention axions. And Babu told me that he also didn't mention axions when he talked about the strong CP problem. I think that can only happen at Maryland, that you can confidently give a talk on the strong CP problem and not mention axions. So I thought I should mention them at least once. So if delta CP is 0, then you have theta bar and delta CP both being 0 or pi. And of course, the axions won't be able to explain that. So they don't pass muster if sign delta CP is 0. So that's why. So in closing, I always admired Dr. Mohapatra for his sense of humor. Once he had, when I was worried about adding 210 and 126 Higgses in SO10 because they are so big compared to this to the left-right symmetric model, he said just take the logarithm. don't worry about them. So his sense of humor and his depth of understanding has always been tremendous. Thank you all.